I have only 3 slides, what with several bullets. Someone asked, so you're done? I said yes, but for the time being. There are a bunch of issues that we really like and possibly have to address in the next few years. And the order that I have is not the order of importance, but these are the issues. After the New Zealand 2 earthquakes in New Zealand, Darfield and the Christchurch, really a couple of very important technical issues came to the surface for the community. One issue is the foreshock, mainshock, aftershock, both in terms of ground motion. Suppose you have a mainshock, what is the probability of aftershock? What is the level of ground shaking in aftershocks? As well as the damage. Suppose you get some moderate damage in, say, hypothetically single-family home, what is the probability of more damage in the aftershock? So there are very challenging, important technical issues for the entire community, both in terms of ground motion as well as damage to structures. I go back. One issue, side issue, not part of ground motion issue. One other issue that came out of New Zealand, and I should mention it, it's not on that list, but it's important, is the issue of liquefaction. Obviously became very serious issue in New Zealand, and outside the ground motion issues here is organizing various geotechs in the West Coast to collect field data related to liquefaction. It's not on my list, it's not ground motion issue, but definitely it's important. Expanding range of applicability of GMPs for lower VS30 as well as to larger VS30. We are now saying VS30s are applicable between 150 or 200 meters per second and higher. There are thousands of sites, obviously in California, single family homes and so on, that are located at lower VS30 values. I'm not talking about liquefiable sites. That's a separate issue. That's not part of this. But even non-liquefiable sites, we like to expand the range of applicability of the GMPs for lower software sites. On the other extreme, we are saying, okay, our GMPs are applicable up to, say, 1,000, 1,200, 1,500 meters per second, but you saw lots of slides that the number of data points that we have at very hard rock is really limited. We like really to expand that, again, for various applications. There are thousands of houses on top of the hills and rock sites. There are dams that are demanding higher VS30 value applicability, nuclear power plants. So really the demand is high to collect data around the world at lowest VS30 value. Unfortunately, we have to, at lower magnitude, we have to go to lower magnitude, but at harder sites. So we like to expand applicability of the GMPs at softer soil as well as harder rock. Becomes high frequency issues and so on also involved, challenging issues. Refinement of modeling for directivity. As I mentioned, we have 5 very good directivity models now. The next step is to use and merge directivity models and the GMPE models, that as part of the estimation and prediction of the ground motion, you have directivity inside. Right now, 1 out of 5 GMPE model has merged these two. We would like to do it more. So in the next definitely couple of years, we really like to merge directivity models and GMPEs together. Refinement of prediction for vertical ground motion. We have, for the first time, very good 4 GMPs for vertical ground motion. Still, there are some issues that we like to address. One issue, the issue that we like to address really are fine-tuning. One issue is that for the basin, like LA Basin, for example, we need to repeat the simulation of the ground motion in vertical direction. For horizontal, we have already talked with the ground motion simulators. Steve Day at San Diego did a great job for us and with us. We wanted to redo that thing, simulation-based amplification of vertical ground motion in basin. It's supposed, hypothetically and theoretically, supposed to be long period motion, but we have to do that. Also, in the current GMP for vertical ground motion, we don't have nonlinearity of the soil in vertical direction. For horizontal direction, we have. For vertical direction, soil becomes rarely nonlinear, but we have to know really the threshold. So these are two simulations that we like to do in the next couple of years. One simulation at the larger scale basin, the other one simulation at the geotechnical level to get the amplification of the vertical ground motion when the soil becomes possibly nonlinear. Beyond elastic response spectra, obviously we are not going to abandon elastic response spectra. They are absolutely important for the entire community. But there are a couple of issues. One issue is that, which is very common in really moderate or large earthquake, no structure, even nuclear power plants locally can become nonlinear. Structure become nonlinear. Now, there are a couple of ways to take care of that, especially one issue that we did a limited study and we published a couple of papers. The period of the structure due to cracks or some degree of damage possibly can elongate, and therefore the magnitude scaling that traditionally we do for the fundamental period at the elastic response spectra, that may have to shift. And there is a sense that that magnitude scaling needs a little bit of refinement. So we want to push it a little bit more into the real world. Once we get some damage to structures, what will happen? On the other hand, there are some issues at high frequency motion, short period structures, and again, I did some measurement of single family homes. Approximately the periods are, depending on the various things, around 0.1 seconds or so. At short periods, especially you get to hard rock, there are some issues with elastic response spectra. We want to readdress that. So short period elastic response spectra, we want to refine that. I don't want to get into the details of that, the issue of kappa and so on becoming important. We want to address that, as well as the other side when you get a little bit nonlinearity. So we want to dig into the issues, how to refine and how to adopt various other versions of a spectra, but we are not going to abandon, obviously, elastic response spectra. Simplification of GMPs, we get huge demand in California, outside California, around the world, that GMPs are now complicated. I want to make sure that the simplification that I'm talking about is not really computational aspects of this. It's trivial. Now with these computers that we have, it's literally before you enter the number, you get the results. So complexity is not really complexity of the GMP couple of pages of equations, because we give you Excel file, Fortran program, MATLAB routine, Python, you name it, Java, whatever you want, we are going to give you. So you don't have to do any programming for this. So the simplification is not that we reduce 3-page equation to 2 or 3 lines equation. The simplification, usually the key issue when you don't know the input parameters that they go into GMPs. One example that Emil showed, for example, if you don't know basin depth, so you have to guess. Obviously, we have some default values. The key is really, in the next couple of years, we really want to examine, assuming you use default values, do we have to pay a price? Hypothetically, in terms of increasing standard deviation. We haven't done this. So we have to say, this is the value, for example, but this is the estimated default value. They go to the GMPEs. what price you have to pay if you don't know. We have to give simplification. We have to quantify the uncertainties and standard deviations if you simplify. We haven't done that. There's a huge demand. In California, relatively, we are in good shape, but not all places in California. Outside the US, huge demand. Constraining GMPs for long period, we are going to 10 seconds. We have much better data at longer period than NGFS1. I mentioned that we reprocess the records. We are in better shape than NGFS1, but we really like to constrain this GMP with some simulated motion as well as with the seismological estimations, because seismologists are saying that they are very good in prediction of the ground motion at longer period. Shorter period becomes more random. So we want to compare the numbers if they're different. I think there are some differences, back of envelope comparison that we did. Why they're different? Do they have to adjust anything, or do we have to adjust anything? Especially now with base isolated structure, lots of other applications for long period, we really want to examine. We didn't have the opportunity to do that and constrain our estimations for long period. Refining estimation of site-specific or single station sigma. We just started. As I mentioned, we have a small magnitude database that we have many sites with multiple events recorded at the same site. We are seeing some trends that we don't understand why, and because of that, we want to dig into that. For the same reason, we have now, as I mentioned, about 10,000 records, small magnitude records in California for single station sigma. This is refinement of a standard deviation in simple word. We want to refine a standard deviation. If there is something that we can take it out, we should take it out. Really, that's the concept. But we still don't understand what's going on. There are some features that we don't understand what's going on. And in data in California, we want to make sure if this is real, we should see it in different parts of the world. Because of that reason, we are collaborating with Japanese, and we are collecting lots of Japanese small magnitude data to see if we see the same trends there, or it's a side effect of various uncertainties. So we have to understand, we have to work on that one to refine uncertainty in the next phase. Taking advantage of simulation of the ground motion, as I mentioned, I truly believe we have the best and the most comprehensive, best quality ground motion database, empirical ground motion database in the world. However, the database that we have, there are some holes in it. A good example is hanging wall football. We have basically 2 earthquakes with well-recorded hanging wall football, Northridge and Chi-Chi in Taiwan. We don't have so many large magnitude earthquakes that with a network of stations over the hanging wall, through footwall, that we see the trend. We don't have it. So we want to take advantage of simulation ground motion to fill the gap. Like anything else, we never want to sacrifice empirical data. Even we get some insight, clue from the simulated ground motion, we will calibrate that against empirical data. That's what we did with hanging wall footwall. We got some clue about the variation of ground motion from simulation. We put it in empirical data, we regressed, and in fact, we modified it. So always at the end, we don't blindly accept anything unless we calibrate against empirical data. But there are examples like this that we would like in the next phase to take advantage of simulation to fill the gap. Topographic effect, and again, by the way, the list that I'm showing you is not my list. I communicate with many groups and various people and so on. This is really a community list. Topographic effects, there are thousands of houses, for example, in California on top of the hills. We don't have so many network of empirical data. VS30, 600 meters per second, top of the hill. Another site, bottom of the hill with 600 meters per second. We say, oh, this is the factor that we have to involve. We don't have so many. We have a really handful of cases. There is a huge demand both for single family homes and on one side And so Diablo Canyon nuclear power plant is on top of the cliff also. So we like to have some corrections of GMPs to include topographic effects. We may have to do simulation, we may have to do something else, but it's challenging, but really there is a demand on that. Besides all the issues that I mentioned related to shallow crustal earthquake for active tectonic regions, there is an ongoing NGA East, which, as I mentioned, is Central Eastern North America, east of Colorado. About 50 people are working on various pieces of NGA East. For the first time, the database, obviously in a stable continental region, we are not going to have so many magnitude 7 and 8 in the database. There is mainly moderate and low magnitude, but the database was very challenging, very messy. The frequency band was challenging and so on. But for the first time, we have a really nice database. We are checking various pieces. Hopefully in the next few months, we are going to post it. We are going to do the same thing that we have with NGA West, another database for a stable continental region, and then GMPs will be developed. We are shooting to finish the whole project of NGA East by May 2015. Then subduction, we have started subduction a year and a half ago, very important. We got seed funding from USGS, then we got a little bit more funding from private insurance industry. This is the part that we need funding to do a better job. The database we are starting from scratch. We never had database for subduction. We got thousands and thousands of records from Japan. Chile, we sent geotechs from USGS 3-4 trips to Chile to do site measurement at the recording sites. They came back. The report is almost ready. We are going to publish it in the next couple of months. So the database is getting, now we are going back to historical legacy data, Mexico earthquake and others. Now we are reaching to the point that we asked CB Cross, he's supposed to send us tapes. I don't know, you're very young, you don't remember. I used the tapes of large tape computer. He's sending us tapes. We have to send it to San Jose somewhere to read it for us. So we are going back to legacy data, subduction legacy data. For the first time, we are compiling a good database of subduction earthquakes. If we get more funding, we like to really do the same thing as we did for West, multiple GMPEs. Right now, the funding is limited. Hopefully, in the next couple of years, we are going to have more funding for that. We are shooting to finish that one by May 2016. This is my last slide, and I appreciate your comments. If you have any idea that I missed it and it's important for the community, send me an email. Let me see. Yeah, my email is here. Send me an email. We really love to hear from you. Thank you very much.